SwayamPrabha. Digital India. Educated India.
Okay, so there we go. So now we're looking into implementation and practicalities. So how do we implement this? How does this work? So there's various ways. I mean, I think there's a million ways you can implement phase field depending on your different platforms and so on. I decided to discuss three: COMSOL, Abacus, and Phoenix. We also done it in our own codes, in Fortran, C++, Julia. You can download them all from the website. But I decided to pick these three just because I think they are the most representative of the whole scheme. So Phoenix will be representative of your own implementation, although it's based on symbolic differentiation, so it's a bit different. COMSOL is maybe the easiest one because COMSOL has it implemented inbuilt, and then Abacus is somehow intermediate and also quite popular. So we published a paper very recently in Engineering Fracture Mechanics that is mostly focused on hydrogen, but it explains basically all the details of how you implement phase field into COMSOL. But as I said, you actually don't need to follow our paper because it's implemented as an inbuilt feature since the year 2021. So it's been already 4 years since COMSOL has an inbuilt feature. And they've been changing a little bit every year. They are working quite a lot in their development. So I don't know if you're familiar with COMSOL, but the COMSOL Model 3 looks something like this. So COMSOL is very similar to Phoenix in the spirit in that it's based on symbolic differentiation. So it was developed by mathematicians, and I think it's actually quite interesting that, the phase field, the finite element codes have been there since the 70s. So it was quite interesting to see that in the years 2000, COMSOL was first part of the MATLAB FemLab. So I think there was some academics in KTH in Sweden who were developing the finite element part of MATLAB. And then they decided to create this COMSOL package. And they used the same idea of the symbolic differentiation. And I think by looking at this problem from a more mathematical point of view, they came up with a very good approach for example, multi-physics problems. Because I think it was difficult to think that a new finite element code could come up 30 years later and compete with the codes of Abacus or ANSYS, where they've been developing for 50 years now, and they had already a well-established user base. But I think the reason why they became so popular is that they use this symbolic differentiation where you don't have to implement things at the low level. You just define your differential equation, and then everything is taken care of. It's similar to Phoenix in that sense. So you don't have to either, Phoenix uses more the weak form, but here you just define the strong form, and then automatically the computer will do it for you. It will identify the weak form, it will then take residuals, it will take stiffness matrices, and so on. So then based on this different approach to finite elements, it has been very easy for them to add extra physics, because they just need to add the PDE, and that's all. So that's why they're good in multi-physics, and that's why they have so many possibilities to modeling coupled problems. Well, for Abacus and ANSYS, it's a bit more complicated, because every time they add a new physics, they need to basically add a new element. They need to code everything, hard-code it, make sure that everything works well, and so on. But anyway, as I said, they have implemented phase field. They had some sort of phase field before for fluid dynamics, because again, phase field can be used to track many other interfaces, but they implemented phase field fracture before. And this is like how the model tree looks like in COMSOL. So you have a place where you define your parameters, your materials. Then you pick your physics. In this case, you pick solid mechanics. And you can pick linear elastic, but also plasticity and so on. They have it coupled with everything. And then you have this other physics called phase field in solids. And when you select these two, a multi-physics nodes appear called phase field damage. And you can see the equations. The equations, you can see they use the H. So it's history field, or it's slightly different. It's written in a slightly different form, but you can see here that they are enforcing a history variable. You can see that they have some sort of degradation function. It's slightly different, depending the formulation is written in a slightly different way, but it's the same thing. But you can see that it seems familiar, right? You can see that the damage stress is equal to 1 minus the damage, this equal to phase field. So it's slightly different in the way it's formulated, but it's identical, basically. And then, basically, you can define the crack driving force. It could be elastic extraneous density, plastic, user-defined. You can define the critical energy release rate. So it's basically clicking a few buttons and you can run phase field studies. It's very straightforward. So there's not much to discuss here. In previous versions, they had it as a node that is built as part of the damage node. So they have a damage node. And when you pick the damage model, then you select here phase field damage. And then again, you pick your strain and release rate, a threshold if you want, the length scale. And you can see again the equations here, the gradient, and so on and so forth. So that's the idea. So they have it implemented already. You just need to click a few buttons and you have access to it. So I think it's the most straightforward. COMSOL have a PDE module where you can basically implement any PDE if you know more or less the PDE that resembles by picking some coefficients. So even before they had it implemented, it was quite widely used in the face field community because it was very simple. You define your PDE. In this case, it's a Helmholtz type equation. So you can pick they tell you the Helmholtz type equation has these coefficients. So you pick your variable, I call it phi, and then I pick C. C becomes L to the power of 2. This is the critical length scale, the characteristic length scale. And then I have an absorption coefficient, a source term that is equal to 2 times history field, blah, 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 and an absorption coefficient that is equal to this. So it's very easy to implement as a user if you don't have access to the phase field, if you have an older version or whatever, or you don't have access to their inbuilt features. But again, it comes already inbuilt. Yeah, that's the idea, because they have a way where they implement everything generally through PDEs by defining coefficients. It's very straightforward to look at the phase field PDE, look at the coefficients and identify them. And this is what they've done in their inbuilt feature. And it's quite general, includes multiple options. You can couple with elastoplastic materials, elastic, and so on. I think so. The benefit is that it's very straightforward to use. So, for example, when I work with colleagues who are experimentalists, they don't want to have a PhD student doing a computation mechanics PhD in order to interpret their experiments. They want the experimental PhD student to run some simulations over the weekend to understand their experiments. So COMSOL provides a very straightforward way, because in one morning, even if you have no computation mechanics expertise, you click a few buttons, you see the results. You learn very, very quickly. So I think it depends a little bit on what you want to do. I think the disadvantages that I can think of is that, phase field is much more robust than any other continuum damage mechanics model or damage mechanics model that I know, or fracture mechanics method that I know. So in that sense, it's quite powerful. But still, there are occasions when you're dealing with complicated problems where you have convergence issues. And COMSOL is a bit obscure on how to handle those convergence issues. So in fact, they have an example in their documentation of how to use phase field. It's an example of they produce some experiments on concrete where you have a crack growing to a hole and then a crack nucleating and growing. And they show nicely that reproduce exactly what you see in the experiments and so on. But if you change a few parameters in that example, then it doesn't converge. So COMSOL has many options for when it comes to convergence. You can do staggered, you can do monolithic, and they have multiple solvers. But it's all often a little bit of I won't say a black box, but almost black magic in that it's a bit of obscure how you pick those numbers to make things work. Well, in other packages, it's to me much more clear what I need to select to get convergence. So anyway, you may find a problem that it may be very easy for you to start starting things, but you may find a problem where you set up your model in 1 hour, you have results 30 minutes later, but then in order to get all the results that you want, you may have to fight a little bit with the solver options, and there are many solver options. I think that's the only disadvantage that I would say. Okay, Abacus is working, as far as I was told, in putting this inbuilt. There's a lot of demand from their users, so they're trying to implement phase field as inbuilt. For the moment, they don't have it as inbuilt, but you can implement it using user subroutines. Abacus has these user subroutines, and you can implement it with that. And there's various approaches. I think like at the same time as others, implemented first with a user element subroutine, but now you can do it with a UMAT subroutine, which is much more easier. And this is what I will discuss today, because a UMAT is at the integration point level, so it's very easy. But let me bring you a bit of up to speed in Abacus subroutines. So the idea is that Abacus is a commercial finite element package. It's written in Fortran, but then they have small pieces of Fortran codes where they say, okay, as a user, if you want to define something yourself, we let you write it in here. We'll give you what we call a user subroutine, where you receive some inputs, and then you need to do something with those inputs, and then we give you some outputs. So there's multiple ways you can define the subroutine. So for example, here, this is the typical flow in Abacus. So you start the analysis, you define initial conditions, you start the step, you start the increment, you start the iteration, you define your element stiffness matrix, you define your loads, and you assemble the system, you solve the system, and so on, right? So you can define this kind of boundary conditions for this kind of subroutine for defining some special initial conditions. You can define, basically most of the magic happens here. As you can see, when you define your stiffness matrix, you can use a user element to define your own element, and then Abacus is basically assembling and solving your system. It's like you're having your own code. And then you can have this user-defined field, you can have this user material to define different constitutive behaviors, and so on and so forth. And if you look at the behavior more at the locally, what you see is when you start an increment, you calculate integration point field variables for another values, you start the iteration, and then in a UL, what you have in a UL is, those of you familiar with coding finite elements, a UL is basically you get the displacements in the nodes of your element. You use the strain displacement matrix to interpolate those displacements into strains within your integration points. This is what you do here. Then you use your strains to calculate at the integration point level, for each integration point, your stresses and your Jacobian matrix, if it's changing. If its elasticity is always the same, but if you have an elastoplastic material, you're getting something different here. And then eventually you get out of your user material and define your loads on your right-hand side. So this is what you do in your user element. Basically, you are building your stiffness matrix and your forces, your nodal force vectors, so your right-hand side, your residuals, and then Abaqus is assembling the whole thing. But if you basically have a new plasticity theory, for example, that you want to define, you don't need to define all of these things. You don't need to define shape functions, strain displacement matrix. You tell Abaqus, give me the strains, I'll give you the stresses and my stiffness matrix. So my Jacobian, my constitutive matrix. If it's Hooke's law, you don't have to do anything. So that's what they call a UMAT. It's a user material subroutine. So Abaqus will give you a strain and I'll say, okay, now I don't know what you're doing, you user, you define your own code, but please give me back my stresses and please give me back this derivative of stress with the strains, which is basically the constitutive matrix. Right? So if you have an elastoplastic material, your constitutive matrix is changing with your hardening every step, so you need to provide that number back. That's the idea. So I think we're going to do a break now because the next part is important and I want you to be fresh. But I think the only thing you need to understand now is that if you think about phase field, so this is the phase field equation that we need to implement, right? So what we first thought and everyone else thought was, okay, we need to do this at the user element level because we have a new value, a nodal degree of freedom. So we need to come up with an element that looks like this, basically, right? So that maybe I'll delete some of these things here. We need to come up with an element where we are solving for. So this is at the element level. So you can, let's imagine that we have a 2D problem. One element, you have ux, uy, and every node. I'm just looking at one node maybe. And this will be fx, fy, and then some sort of, call it S phase field maybe. And then you have here your stiffness matrix. I mean, it will just be all related to displacements. And then you have a phase field one. And what you do here is to be discussed later, whether you do coupling terms or not. But anyway, so you say, okay, normally when I do finite elements, I just solve for ux and uy. So now I need to do something else. I need to add an extra degree of freedom, like if I solve for temperature. So necessarily I'm going to have to define my own element. This is what we all thought. So Abaqus will not be that useful. I mean, you'll still use Abaqus for meshing and pre-processing and post-processing. But at the end of the day, I need to define my own user element. And that's a bit nasty because in Abaqus, when you work with user elements, you need to, you cannot use most of the inbuilt features of Abaqus because Abaqus doesn't know what are your shape functions, where are your nodes. They don't know where your nodes are, but that's the only thing they know. They don't know how even the geometry of the element. It doesn't know anything, whether you're using Lagrangian element, serendipity element, you don't know anything. Abaqus doesn't know anything. So a lot of, for example, the contact options of Abaqus do not work. The visualization options of Abaqus do not work. You need to do some tricks to visualize things. You use typically a dummy mesh. So it's a bit messy, but I mean, this is what we thought we had to do, right? Because we said, okay, we need to implement things. We need to add an extra degree of freedom. So for sure, we need to define our own user element, and this is the way we implemented these things first. So we basically come up with a Fortran code where we reproduce first the Abaqus elements and displacements, and then we said, okay, now we add an extra term that will be that stiffness matrix and residual associated with the phase field. So we took the phase field equation, we applied a weak form, and then we derived the residuals and stiffness matrices. That was the idea. And that is, of course, a long code, and it's like doing it in your own infinite elements. But there's another way, there's a clever way that you can do it using only a user material subroutine. So going back here, so you can use everything that is inbuilt in Abaqus. Abaqus will give you a strain, and then you do something, and you can get it out. But I'll tell you that after a break. So it's 10, let's say 5 past 10, we're back, and then we'll discuss that option. Okay, thanks. Okay, back to business. So as I said, you can implement it in let me remove this thing. There you go. So you can implement it into Abaqus with a user element, well, like you will do in any other finite element code. But the goal that we were hoping to is there a way that we can implement it much more easily, in a way that we can take advantage of the inbuilt Abacus features. And this will be very convenient, not only because it will make it very easy for people to use. You don't have to do anything special. You don't have to play with the mesh and add an extra degree of freedom. You could just use Abacus in any way that you normally do. And the way to do that is by taking advantage of the thermal analogy, because Abacus, like almost all commercial finite element packages, I think, COMSOL is a bit of an exception in that it can handle many multiphysics problems. But, thermomechanical problems is something that all commercial finite element packages can handle. They all have elements, special elements, to solve for this plus temperature. So if we can make a way, if we don't care about the temperature, and we'll later discuss what happens when we care about temperature, but if we don't care about temperature, is there a way that we can use the temperature as if it were the phase field? That's the idea. And this is something that we explain in these 2 papers here, so you can take a look, but I'll tell you a little bit more today. So the idea is that at the end of the day, this is the system that you want to solve. So you want to solve for the displacement and the phase field. So normally this involves defining a displacement stiffness matrix, a phase field stiffness matrix, and some residuals. The way you normally do this is at the element level. But if we can do it at the integration point level, then we don't have to, we can use all the inbuilt features of Abacus. We don't have to write very long codes. And the way to do that is by exploiting the heat transfer analogy. So if you have, remember this is the phase field equation, and I'm going to rewrite it as this. It's the same thing. I'm just moving terms around. If I look at the steady state heat transfer equation, then it looks something like this. This is for the steady state. So this is an equation that is inbuilt in all finite element packages. So you can see that the analogy is quite straightforward, right? So if I make my thermal conductivity equal to 1, temperature seems similar to phase field, and then I just need to define the source term, which is this one here. And then also, of course, Abacus will ask you for the derivative of the source term with respect to the temperature, which is the derivative of R with respect to phase field, which is something like this. So basically, this has made our life very easy, because the heat transfer problem, which is, can be expressed in quite a general way in Abacus and other packages, you can do a transient, and I'll discuss later why transient can be useful on occasion. But you can also do it in a way where it's a steady state. So you just click a button in Abacus or in ANSYS or any other finite element package and say, I want to do steady state heat transfer. And when you do that, Abacus says, okay, no problem. Then the equation that we're going to be solving is this one. You're doing a couple thermomechanical problem. In the difference that here you're using the temperature as the phase field. You don't care about the temperature. The temperature has no physical meaning. It's just your phase field. The only issue is, of course, when you have thermomechanical cracking. Then you need to think about something. And I'll discuss that later on. We have also a solution for that. But this is very nice, because then we can do things at the integration point level. In fact, depending on the version of Abacus, you need a head val, or only in a UMAT. In a UMAT also it allows you to define an R value. And I'll show you now how it works. So you only need a 50-line user material code, a UMAT code. So I don't know if you're familiar with UMATs, but UMATs are the subroutine for user materials into Abacus. So Abacus, as I said before, when you're dealing with a UMAT, Abacus basically is here. They give you the strains, and they tell you, please give me the stresses, please give me your material Jacobian, so your stiffness matrix. So Abacus will say, I'm giving you a variable called stress, please update this guy. I'm giving you a variable called DDSD, this is the stiffness matrix, please update this guy. If you were to implement linear elasticity, you will never, it'll be a constant value because it doesn't change in time, but the plasticity will change, of course. And then if I'll give you, and for you to update these 2 guys, I'll give you some state variables if you want, and I'll give you some strains, that's the strand variable, and D strand, that's the increment in the strain, and some other things. It will give you some coordinates, some other stuff that you may want to use, and some properties that you may use. And it gives you temperature, and increment in temperature. So that's the idea. So then what do? This is the code that we write. So this is by the way, what comes with Abacus gives you. Right? This is Abacus tells you all UMAT need to start like this. So they give you strains, change in strain, temperature, that means phase field. We're going to use the temperature phase field, change in temperature, and some user-defined constants. And they're asking you for the stresses, your constitutive matrix, your temperature, your phase field, your source term, and the derivative of the source term with respect to temperature or with respect to phase field. So what do? First, we initialize. We say, this stiffness matrix is going to be equal to 0 everywhere. Then we, as a user in Abacus, you put some user properties that you then use in the UMAT. So one is, for example, Young's modulus. The other one is Poisson ratio. If you were to define in a user material subroutine linear elasticity, we'll just use these two. The other one is a phase field length scale. In this case, I need a phase field length scale. Remember, what are the inputs to my phase field? The other one is your toughness. So that's all the 4 inputs, right? What else do you need? Here, we just need phase field, length scale, toughness, and that's all. And then, of course, you have an elastic material, so Young's modulus and Poisson ratio. 4 inputs. It's very simple damage model. So the first thing is COMSOL is giving me the temperature at the beginning of the increment and the change in temperature. So I'm going to put them all together and say, okay, this is the phi variable, the last version of the temperature. Then I'm going to build my stiffness matrix. So here I'm using the Lamé term, so shear modulus and lambda, so mu and lambda. So this is, the expressions. This is elasticity. You all know this very well. So you compute elasticity, then you fill in the terms of the stiffness matrix, and then finally this is what you will do basically if you only had elasticity, right? So you will compute the stiffness matrix, and then you will sum up. COMSOL gives you the increment in strain because COMSOL has solved for the displacements and calculated already with their own shape functions the increment in strain. So you'll update the strains with the increment in strain. This is total strain, and this is the stress. You'll have calculate. It will be a multiplication of the stiffness matrix by the strains, right? So I'm putting this here. So using Boyk notation, we're using Boyk notation. COMSOL uses Abaqus uses Boyk notation. So assuming a 2D problem, this is this is actually written in a general way because n tens is number of shear terms, so to say. So it's written in a 3D way as well. But anyway, assuming 2D for the sake of simplicity, you'll have something like this. This is your stiffness matrix, your elastic stiffness matrix. These are your strains, these are your stresses. So basically, you are building this. You have Young's modulus, you have Poisson ratio, you can define the Lamé coefficients. Very straightforward, the same way you will do in elasticity. Then you have, I'm sure you all learned this at some point. Then you have the updated strain. So Abaqus is giving you the strain and the increment in strain. You just update, very straightforward. Stresses is multiplication of your stiffness matrix C multiplied by the updated strains. That gives you stresses, all good and easy. So that's half of your subroutine, you're already there. Then the next step is to calculate so we are in line 30, we reach here line 38. Now we go line 40. You see, this is the end. This is the whole subroutine. It can be as simple, it cannot be easier than this. So you calculate your stiffness matrix, you update your stresses and strains, and then you have only here 20 lines left. So the next step is that you calculate your strain density. I'm going to call it psi. So first I initialize it, and then remember the expression is 1/2 of the multiplication of those tensors. So you multiply each component, so stress 1, multiply strain 1, I'm using this Boyk notation. Then stress 2, multiply strain 2, multiply by 1/2, and so on. So I calculate my strain density. Then I degrade my stresses and strain density. Remember, the ones that are at the end, the ones that I need to send to Abaqus are the degraded ones, otherwise phase field is not doing anything. So I have my degradation function that is 1 minus phi to the power of 2. I multiply that by the stress. 1 minus phi to the power of 2, multiplied by the strain density. Remember, this is the degradation function that we're using. Remember the force equilibrium, the balance of linear momentum. And then finally, I have these 2 lines. So my entire phase field implementation is these 2 lines. Plus, of course, using the phase field to degrade my stiffness. Everything else is the same as in linear elasticity. So these 2 lines. Abaqus knows that I'm doing a thermomechanical problem. So Abaqus is asking me for my R, my source term, Abaqus calls it RPL. And then it's asking me for my derivative of R with respect to temperature. So if I go back, this is the phase field equation. I just reformulated things around. This is the heat source equation. So I already told Abaqus in the input file in the CIE that K is equal to 1. And now I just need to define R in the user subroutine. And R is basically this. So I have this line that says R is phi divided by L minus 2, 1 minus phi divided by GC XL multiplied by C. And then the derivative will be 1 divided by L to the power of 2 plus 2 multiplied psi divided by GC by L. That's all I need to do. So it's very, very straightforward. And the code is there. You need to develop. You can just use it as you wish. In Abaqus, this basically means that in Abaqus CIE, you click user material, you do a thermomechanical analysis. We have instructions in the website. You can find them all. But you do a thermomechanical analysis. You click user material. You define your 4 properties, Young's modulus, Poisson ratio, length scale, GC. And that's all you need to do. And you use this subroutine. But you can see that it's very, very straightforward. The simplest UMAT you can think of.
It's UMAT HT, right?
No, this is just UMAT. So I should clarify one thing. Since 2020 version, I think it is, Abacus, before, if you wanted to do something related to temperature, you had to do it in either a UMAT HT, which is the UMAT for heat transfer, or a HETVAL, which is some sort of heat generation subroutine. And since 2020, the source term and the derivative of the source term in a heat transfer problem can be defined in the UMAT as well. They have this RPL and this DRPL with respect to temperature. I don't know if this was always been there or they changed the interface, but I do know that we had to use the head valve, so you are not, probably they changed the interface, I guess, since 2020, yeah. But so it's basically all in a UMAT. We also use the UMAT HT, but we do that when we want to do more complicated phase heat, for example, for phase heat corrosion and other things, where we need a more general description of the heat transfer problem. And also when we want to do, for example, thermomechanical cracking. So we have multiple variables that we want to solve as temperature. That's the issue. So I'll eventually show you a UMAT HT as well.
So we are degrading the HT matrix here, no?
Yes, yes.
Automatically the stress calculation will be degraded only. So why additionally we are giving
You are, say that again, you are degrading the...
DD, SDD, like stiffness matrix we are already taking 1 minus 5 square term, right?
Yes.
So automatically when we will calculate the strain with the degraded stiffness matrix, stress will be degraded only.
The stress, yes. So what we're doing here is we're degrading the stress and the stiffness matrix. You could calculate your stress from your degraded stiffness matrix. It will be the same, and it will give you the same result. Yes. So I think in this case I wrote it this way just to make it simpler for people to know that this is exactly what you do in elasticity. But you could degrade already the DSD here, and then calculate the stress with the degraded stiffness matrix. I'll give you the degraded stress. So that's also fine. Yeah. It's the same approach. It's just I wanted to put like a piece of code that everyone will say, oh, I've seen that before. This is, the typical example that Abacus gives me for a UMAT of linear elasticity, which is a simple one. Just to say, okay, then the only thing you need to do is degrade your stresses and stiffness matrices, and then give Abacus the source term and the derivative of the source term. So it's 2 lines that you add to your UMAT, maybe 4, if you count the degraded ones. That's the idea. Yeah.
The site that you are calculating, you are adding the strain energy density at all the nodes, to my understanding.
So this is all, user material subroutines are done at the integration point level. So Abacus will that's the beauty of them. So that's why they're so simple. So Abacus will calculate from the nodal values. We'll use whatever shape functions has in their inbuilt elements. We'll give you, they will say at each integration point, you can define your own material constitutive law. I will give you the strains in that integration point. So here, this is, for example, MPT is the number of the integration point. So Abacus, for every integration point of every element, they will call this code that you have, and they will tell you, okay, I'm giving you the strain, give me the stress and your stiffness matrix.
What we get is the strain energy or strain energy density?
We get a strain energy density. We're calculating strain energy density.
Even after adding all those.
So we're just doing one. So remember the derivative of the strain energy density. If you think of 1D, you just remember if you have a uniaxial linear elasticity, this is the behavior of your bar. The area under the curve is the strain energy density, so it's 1/2 of the triangle.
C is also a field quantity. It has its own values at different points.
Yes, this changes in space. Yes.
Whereas the strain energy is not like that. It is one quantity, but at a given volume.
Yes, you multiply the valve volume, you get a strain energy. That's correct. So this is a strain energy density. This is what comes into the phase field. So the phase field has a strain energy density there.
When you are adding the different values of psi at different points, different integration points, what you are maybe getting the strain energy is my doubt.
We're not outing values for different points. We're calculating this at the integration point level. We're calculating for every point. So we're solving this locally at every point. So you're calculating the strain energy density in every point, and then that drives the fracture, basically. That's the idea. So that's all you need to do. And that's all you need to do in Abacus, and we'll show some examples later, but that's all what you need to know. Yeah.
So earlier we spoke about this splitting, right? Strain energy splitting.
Yeah.
So if I implement it in UMac, how do I take it?
So that's a good question. We do have the codes for that. Basically, what we do is here replace this very simple expression with we call our own subroutine where we say, okay, you add a flag variable and you tell me you want to do volumetric deviatoric, spectral, no tension, whatever you want, and then you calculate this C quantity in a different way. It's a different expression. It's just changing that equation. But we do provide a code, what we call the generalized code, which has not only 81, 82, and phase field coefficient models, but also different splits for each of those models.
So this thermomechanical thing in Abacus, will it solve it in a staggered manner or monolithic?
You can pick. That's a good question, and I didn't discuss that. Maybe I should have put more details about this. I guess I wasn't sure how many people will be Abacus friendly versus other tools friendly. You can solve it in both staggered and monolithic. I think the only thing is that yesterday I discussed about this quasi-Newton monolithic, which I found the most promising avenue. That one is not available for this thermomechanical problem in Abacus. So you have to use a user element for that one. But you can solve both monolithic and stagger with the problem here. So that it works quite well actually. I think this is to me it depends on the application which code we use, but this is I think the most popular code that we have. So a lot of people I know are using this code. It's because it's very, very easy to use. And then you can use everything that is in Abacus Contact, any other feature that is already built. You don't have to, when you use user elements, you need to do something with the user input to make sure that you have an extra mesh or to visualize things. Here you don't have to do anything, just everything comes naturally. It's very, very simple. Yeah. Yeah.
So the del dot, the 1 minus pi square sigma is to be the solve, right? So the sigma there is a spatial function. So sorry, the p there is a spatial function. So it depends on the space. So
yeah. So think of phase field as temperature in a way, because this is why we're using the analogy, right? So temperature will change in time and space when you're solving a problem where you have heat transfer. Your temperature is changing in time and space. So the phase field is changing in time and space. So you would get, that's why you get cracks evolving and so on. So you will be, your phase field, so Abacus is calling this code every integration point. So you may have, this will be discretized with many elements. Each of these elements will have integration points, whatever integration point. So for every point, Abacus is calling this code. Abacus is telling you for each of these, what is the strain, what is the temperature, solving those two equations, the steady state heat transfer that is actually, we have cheated Abacus and told him that is the phase field equation. And then you go into this code and tell Abacus, okay, based on the strain, this is my Jacobian matrix, so the constitutive matrix. This is my stress, and also based on the temperature. And this is, of course, we also need to define this source term and the derivative. That's the only thing we need to do. So it's changing in space. Yeah, you'll get a different number. Your strain unit density is changing in space. Your phase field is changing in space and in time. So every iteration of every increment, Abacus is calling this code and is updating everything. That's why you see, the phase field evolving and this type of stuff. Correct. Yeah.
So when we say it's basically a function, right?
It's a field quantity. It's like temperature in a way.
Like in a temperature.
Yeah.
So when I say 0 and 1, what do I actually?
So it's a field quantity like temperature. It's just that the way the PDE is constructed, it will only allow phase field to go between 0 and 1. So it's like if you had a temperature problem that the way it was constructed, temperature will only change between 0 and 1, and then the meaning is similar to a damage variable. You can think of a damage variable will also go between 0 and 1. So I guess the most similar thing will be non-local continuum damage mechanics models. In those models, you will also have some sort of damage variable that will have a gradient term somewhere and will be evolving independently, and it will be from 0 and 1. So that's the idea. So I don't know if that answers your question.
Actually, when you say like in heat transfer, you have input variable as temperature, which is the phase field.
Yeah. So Abacus thinks that it's solving a heat transfer problem. Abacus thinks that it's solving a thermomechanical problem. But because the equation is so similar, I can say, okay, if I make this k equal to 1, if I make this r equal to this term here, what Abacus is going to be solving actually is this equation, with phase field being the temperature. So Abacus is solving at the nodes Abacus is solving a problem that is coupled displacement temperature at the nodes, and it's giving you temperature, but in reality it's actually the phase field because it's solving the phase field equation. So it's a problem where you assume temperature is not important to you because there's no other coupling, so there's no thermal strains or anything that you are activating there. Everything the couplings are defined in the UMAT, you define the couplings. So in that sense, you are not, the fact that you're cheating Abacus with temperature doesn't have any other implications. Abacus thinks that you're solving by temperature, and Abacus has some inbuilt elements that can solve couple thermomechanical problems, but then you are actually solving for phase field. So when you plot quantities in Abacus, you plot temperature, and what you see is the phase field. So you see something that varies between 0 and 1, you see the cracks, all this type of stuff. That's the idea.
So you multiply that with the variable you want, then you get the like I want to see the temperature variation spatial in my specimen. So if I get my phase field and I just multiply with the actual temperature, will I get the variation?
So Abacus will solve for temperature, thinking that it's solving a thermomechanical problem, but it will actually be solving this equation. So what you will get as a temperature distribution will be your phase field distribution. And there will be no temperature whatsoever. So you say, Abacus, plot me temperature. It will actually, you will see something between 0 and 1 with all the cracks going around, and there will be no temperature. If you want to get temperature, you can't because you are not really solving any realistic heat transfer equation. You're just solving a phase field equation.
Just for curiosity, how is the P bounded in the UMAT? So are we explicitly saying that when the damage parameter exceeds 1, we reset it to 1? Or
No, we don't do any of that. I've seen some people sometimes do that in the UL, but it's just, it's the equation that you're solving for that will bound it necessarily. So it will not. So phase field can only be 0 or between 0 and 1 based on this. So you don't have to bound anything. This is the whole UMAT. This is the entire UMAT.
external intervention required to bound it?
So you don't have to. No, you don't have to specify any bounds in the UMAT or anything. So it will just.
Are there circumstances where this may go up? I mean, I'm just speaking hypothetically here. I'm just curious.
I have never seen. I think I've seen on occasion some plots where it will go beyond 1, but it was mostly interpolation within the elements or something that maybe had an element very big, very distorted, or things like this. So it will not go. It should not go beyond 1. Yeah.
It's inbuilt.
Yes, exactly. Yeah. So this is the entire UMAT. This 50 lines, and I'm saying 50 lines, but actually most of the lines are, the UMAT interface is 10 lines that you are doing in there. It's all in there.
By the formulation, is it not solving in monolithic?
You could solve monolithic, so Abacus allows to solve thermal problems in a monolithic or staggered way, thermomechanical problems. So the same, you can say, you click a button and you say, Abacus, I want to solve my problem, which is not real thermomechanical problem, it's a cheated thermomechanical problem, monolithic or staggered. In which case, Abacus will add some coupling terms. But it's, I know this one, I don't think Abacus has coupling terms because you don't define those coupling terms. So, but in any way, you can solve both at the same time or both sequentially, one after the other. Yeah. So Abacus will have an option there to solve staggered or monolithic. Yeah. Okay, so that's when it comes to Abacus. If you want to do your own code, this is what we did here. Again, working with 2 academics here, and Hirschikes was a PhD student at IIT Madras here at the time. We did it in Phoenix. Phoenix has kept evolving, so I don't know. We did it some years ago, as you can see. I don't know if this code still runs because every time they change. I like Phoenix very much because it's open source and developed freely by academics. But one thing that I didn't like before is that they would not enforce backward or forward compatibility. So every time there's a new version, you need to change a few things in your code. So I don't know if it will still work, but I do get emails from people using this code. So I believe it's working with very little details. So now this is a full finite element code. This is it's a bit longer, but it's only 100 lines. It's not that complicated. So we can go through it as well in case you want to do it in Phoenix. So this is the code. This is the first 50 lines of the code. It's also relatively straightforward because it's based on the symbolic differentiation. So first you import from the Dolphin package. This is a package that Phoenix uses to use symbolic differentiation. Then you read your mesh. Normally you define your mesh with an external package. I used to do it with Abacus, but I also use sometimes Gmesh or other techniques. Then you define a discrete function space over the mesh for a scalar field. And in this case, we used first order Lagrangian finite elements, but you can pick other things if you want. So you basically create a function space. So Phoenix is written by mathematicians, so it reads very much like that. But if you're used to Phoenix, you'll see that it's very straightforward. This is what you normally do anyway. Then you define another function space. This is kind of a vector function space for the vector field, for the displacement field. And we use, in this case, the same discretization, linear discretization. All those things, of course, you pick in Abacus. In Abacus, you can pick thermal, mechanical elements that are, first order, second order, and so on. You also project the history field. So you also need to define a function space. Then you define two trial functions. Again, Phoenix very much mathematical-like. So you think of a weak form. So it's a bit more complicated than COMSOL in that sense. You use the weak form, so you use a test function. You define a phase field, P, and a test function Q, that is the delta phi, over this function space V. Then you define a test function, a trial function, the displacement field U, and a test function delta U, or V, in this case we call it V, in the scalar function space V. You assign the material properties, so one line per material property, GC equals 2.7, L 0.01, lambda 1, whatever number you put. This I'm defining now in this case the Lamé parameters directly. I'm trying to remember what we normally do break at 10:30, right? So we're gonna maybe I'll finish this Phoenix implementation just to not leave it in the between, and then we do a break. I don't think it should take that much. I'm going a bit fast because, for those of you who have not seen Phoenix, this will sound all like Russian, and for those of you who are familiar with Phoenix, it will be quite straightforward. But I just want you to get a taste of, how this kind of code looks like. So then you define the strains as a function of displacement. So you define epsilon u being the symmetric part of the gradient of u. So again, written very mathematically, you can see. Then you define the stress as a function of the strains using Hooke's law. So sigma u, which is basically, this is the Hooke's law using Lamé coefficients. This is the identity matrix. Then we define the strain energy density. Here we're using, for example, the volumetric derivative split. So you can see that the way we calculate psi is a bit different because you have this a bit extended version because we're using this volumetric derivative split. Then we enforce the reversibility, the H. So we say, if C old is lower than new, then we take the new. Otherwise, we take the old one. This is the kind of approach. Then we define a domain to apply the boundary condition. So you need to tell Phoenix, okay, here there's a border. Please apply a boundary condition there. We call it top. We define a region in the bottom that we call bottom. We apply boundary conditions. We do apply phase field equal to 1 in this case. So we define a region called crack, and we tell, based on these coordinates, this region is going to be the crack. Then we use a user expression to define the load. So we say the load is going to increase in time. So it was from 0, 0, it's going to be called load. And then I'm going to say that the load increases. Then you apply the Dirichlet and Neumann boundary condition. So in this case, in the top, I'm going to prescribe the displacement of, in the bottom, I'm going to say U doesn't move. I'm going to fully constrain my plate. In the top, I'm going to say Uy has to be equal to this load. We group these boundary conditions in a variable that I'm going to call more easily.
Is it phase field initiated?
Yes, in this case, we phase field initiate. So here we first define the crack, and then now we define, you can see the boundary conditions for phase field in this region called crack as 1.0. So in this case, we define the crack using phase field. You could have done geometrically. In this case, we did it with phase field. You initialize all boundaries. You define this measure ds to calculate the normal to the surface. You calculate the normal to the surface. You define the solution space. These are very standard Phoenix type of equations, or Phoenix type of procedures. You define the solution space. And then this is when the more interesting part comes. You need to solve the weak form of the problem. So you can see the displacement problem is basically 1 minus the phase field to the power of 2 multiplying the inner product of the displacement, the gradient of the displacement, so the strain multiplying by sigma. This is the idea. And then you define the phase field problem, which is this equation here. So this is the weak form of the equation. We haven't shown them before, but it's relatively straightforward to derive them. We have it in all the papers. So again, you do GC multiplied by L by the product between these two. GCL, you see the gradient of these products. So it's all very much written like in the weak form that you see, right? So it's very relatively straightforward as well. And I'm already here, by the way, in the bottom of these 50 lines. And then you use something called linear variational problem to calculate your new problem, and then linear variational problem to calculate your new phase field. So to solve both. and then you, in something called solver disp, you store the code to the linear solver to obtain the displacement. I'm going a bit fast, but it's, again, I don't think it makes a lot of sense to go very slowly. It's just for you to get a taste of how it looks like. And then in this solver file, you call the linear solver to obtain the phase field. Basically, this is the whole thing. I'll show you first the first 50 lines. This is the other 50 lines. You can see. Maybe we can go through it together. First, you take the mesh. You define some function space, some trial functions, so phase field displacement, the test function, test displacement. You introduce your parameters. You define your constitutive function. So you say, my strengths are going to be the symmetric part of the gradient of displacements. My sigma is going to be all of this multiplication by epsilon and displacement and so on. My strain energy density is going to be this. And then I define my history field, as you know. Compare my old with my new one, and I take the biggest one. Then you define the domains where you apply your boundary conditions. You define your boundary conditions, your displacement and phase field boundary conditions. Then you solve your problem, so you express your variational form. And now you start the iterations. You say, okay, I initialize. My time is going to be equal to 0. Displacement is going to be whatever displacement I want to apply. My time increment is going to be 0.1. I define some tolerance. And then I start here calling this thing. So I said, okay, we use a stagger scheme. If time is lower or equal than 1, so I start iterating over time from 0 to 1 with these increments of delta t. I actually reduce here the increment a bit because I want to capture very nicely the softening part. But then I say, if my error is bigger than my tolerance, please iterate over this. Solve the displacement problem. Solve the phase field problem, so it's a stagger. I solve first one, then the other. Compute the error using the L2 error norm of the displacement problem. Compute the error of the phase field problem using the error 2 norm, so I compare the previous and the new solution. Compute the maximum error. Compare my error to my tolerance. If it's smaller, run another iteration. If it's larger, sorry, it's done. If it's smaller, it's done. If it's larger, please run another iteration. And then I also compute the reaction forces and so on. So I think what I want to say is that, of course, it's much more messier than the Abacus one. But if for whatever reason you want to use your own implementation, maybe to have more flexibility, or maybe to be able to run maybe very large-scale problems where you want to parallelize things quite a lot and you don't have infinite Abacus licenses, this can be also quite powerful. And as you can see, it's not that complicated. Of course, if you need to add now contact, then that's another story. But the Phoenix community is quite large, and there's people working on a variety of problems, so often you'll find codes here and there. And if you only want to solve the phase field problem, you can see that it's relatively straightforward. You define your 4 parameters. It could be Young's modulus, Poisson ratio, GC, and L. You define your function space. You import your mesh, so you need to mesh somewhere else. People use quite a lot of Gmesh. It's a very powerful open source tool. You define your constitutive equations, and this won't change. You can just copy and paste. You define your boundary conditions. This might change depending on your problem. You apply your solution, and then basically you solve each system. You calculate the error. You iterate until you get a solution. That's the idea. That's all you need. Okay, so well, maybe I'll stop now, and then I'll come back, because this is some convergence tricks and so on. I think I only have, that's the last slide. Okay, let me do this last slide, so then we cut the video in the right time. So some convergence tricks. That's the last slide of implementation details. So in general, as I said, it's a very robust method. It's by far the most robust I know, so it really works very nicely. However, you may encounter problems where you have convergence issues. It's not unheard of, particularly if you have, for example, yesterday I was discussing with some of you the effect of plasticity and phase field. So phase field converges nicely, but because plasticity, you are solving an internal Newton-Raphson algorithm to determine whether you're in the yield function or not. It might be that the internal Newton-Raphson for plasticity is completely lost, because suddenly you had a situation where a crack was growing stable, and suddenly the crack grew in an unstable fashion, and a point which had some low current capacity, the next increment has no low current capacity anymore. So the plasticity algorithm is lost because the solution is, the stress field is very different from the previous iteration and is completely lost. So some things like this can happen. So there could be problems where you get convergence. In linear elasticity, I don't remember ever encountering any convergence problem if you use the right solution schemes. So what can you use? So monolithic quasi-Newton is an approach. It's something we champion in my group, and we find it to be the best. That being said, you may not have access to a monolithic quasi-Newton scheme for whatever reason. So a lot of people in the community use staggered. Single versus multipass. Multipass is a bit more rigorous, one could argue, because you don't lose completely on conditional stability, so you retain a bit of these capabilities. You don't go fully explicit, so to say. Single pass So if you have a problem where multipass, my advice will be, if you have a problem where multipass, try multipass first. If you have a problem where multipass doesn't converge, then go for single pass. Just being careful, knowing that you may be sensitive to your time increment, like in any other explicit scheme. So you may have to do a time increment sensitivity study just to make sure that you're not deviating for the right solution. Then the other thing is that you will see that in many papers, the degradation function is defined not only like this, but they add a small term here, that's sometimes called kappa or k. This kappa or k term basically is intended to make sure that when your phase field is equal to 1, when you have a fully cracked material, you don't lose completely the well conditioning of your system. So your stiffness matrix knows completely 0. So this can be useful. For example, if you imagine, I don't know, a large strain elastoplastic problem, if your elements have no load carrying capacity, they're going to be extremely distorted because they're going to deform all over the place. So retaining a little bit of load carrying capacity is good. And initially, I started using 1 to the minus 7 with this one. And I found out that it was good. It will give you an extra bit of convergence capabilities, and it will come at no effect whatsoever because 1 to the minus 7 is still very small. So you won't see any effect on the force displacement curve, on the crack trajectories. Everything will remain the same. However, when dealing with some problems were a bit challenging, in particularly with elastoplastic solids, I realized that other groups were using much larger numbers. I saw, well, I will not say names, a group using 1 to the minus 4. I used 1 to the minus 4 after following that group. And I was actually, the effect on the results was also negligible. You couldn't see it. I mean, you could see if you start looking at, decimal numbers. But if you plot force displacement or crack trajectories, you couldn't see it. So it still was, you have a big difference in orders of magnitude of your stiffness of a damaged versus undamaged material point. But it retained that, so your damaged elements were not that distorted. So that was good. So again, this you can play with. Again, you can start increasing it progressively, but making sure that it's not affecting your results. So that's another approach. Some people use this viscosity coefficient. I never use this one, and I'm not a big fan of it. This is something people also use in Cuisson elements, this kind of viscous dissipation. The reason I'm not a big fan of it is that I don't think it's physically sensible, in the sense that the damage, your material can be rate dependent, but the damage process is not rate dependent. How you separate those two atoms apart is not related. It's driven by a potential. It's not. But I mean, different people have different opinions as well. It becomes a bit of a philosophical discussion. The thing is that Christian Mie first used this, I think. So he added this extra term to the phase field equation, and that basically, regularizes your problem a little bit in such a way that convergence improves quite significantly, depending particularly on this value of this viscosity coefficient. Christian Mie showed that if you pick values that are sufficiently small, on the order of 10 to the minus 7, you gain convergence and you don't really distort that much your problem. However, one has to be careful, because if you use sufficiently large values, then you get a bit of an impact there. The way you want to implement this, for example, into Abacus, is that instead of picking a steady state heat transfer, you pick transient steady transfer. And then you have a problem like this. This is what Abacus gives you. So you say again k equals 1. You again define your source time in the same way in the UMAT. But now you define the density. Maybe you define density equal to 1. And this kind of heat capacity coefficient, you define it equal to whatever you think your eta value should be. That's the idea. So these are basically the three key takeaways. I will recommend monolithic quasi-Newton. If you can't, it's easy to use in Abacus, but if you don't use Abacus for whatever reason, or you want to use ULs, staggered. Single pass, more robust than multipass, but careful with the time increment. This well-conditioned parameter I typically always implement it with 10 to the minus 7, which I know is small enough, but you can ramp it up, again being careful that your results don't start looking funny. You can do a sensitivity study and make sure that it's giving you the right results. This I haven't used, but I would say is the third tool that you have in your toolbox to tackle convergence problems. There's a viscosity coefficient here. In Abacus, it's very straightforward. When you do the heat transfer analogy, you just say, instead of steady state, transient, and then you define your density equal to 1 and your heat transfer coefficient. This is heat capacity coefficient equal to whatever value you want to give the eta. Again, do a time sensitivity study. So that will be my receipt to, if you encounter convergence problems, follow these steps. And then I will be very surprised if at the end of the day you cannot find something that converges after looking into these things. Questions so far? Okay, if not, I think we can stop until 11:15, and we catch up now because we are now on the same track. So I think we'll be able to be in good time. Perfect. See you now.